So I think we are ready to start the afternoon session on convection-permitting, models. Actually, the first talk is by Andreas Prein. The talk is different from, the title is different from the one you see here, because I asked him to give an overview of these types of modeling, especially because he wrote, he was the first author of a very nice review paper in Reviews of Geophysics, I think. So he's going to give us some overview on that topic. Thanks, Andreas.
Welcome, everybody. So convection-permitting climate models are very promising tools because they enable us to provide more impact-relevant, more local-scale climate information. And on the other side, they're very promising because they can or might reduce the uncertainties in our climate projections and can resolve long-standing errors in state-of-the-art climate models. So, as Filippo said, this is a review based on our paper from last year in Reviews of Geophysics. And we will basically cover three main topics. So at the beginning, I will talk about a definition, what I mean with convection-permitting climate models. Then I will talk about model setups and the major challenges in this kind of simulations. And then the main focus will be on the added value, what you can expect if you go to this very high resolution. So let's get started. The phenomena that we are interested in resolving in our models is this guy here. So this is deep convection, cumulonimbus convection. And in fact, in our state-of-the-art GCMs, and also if we look at something like the high-resolution CORDEX simulations, we are not able to resolve this process explicitly. So what we have to do is parameterize this deep convection. And deep convection parameterizations are a major source of errors and uncertainties. However, if we go to higher and higher resolutions, we start to resolve this process. And this is what I call convection-permitting models. And the threshold here is approximately 4 kilometers and less. So to give you a feeling what this kind of models are able to do, I wanted to show you this animation. And basically what you can see here is a May outbreak of deep convection in the central United States. And there are two maps. One is an observational data set, and the other one is coming from a 4-kilometer WRF simulation, which explicitly resolves deep convection. And I just want you to quickly guess which one is the observation and which one is the model. And in fact, it's not so easy. Except if you look over the ocean, then it's pretty obvious because you don't have radar data over the ocean. But this one is the WRF simulation. And the point that I wanted to make here is that the spatial structure, the intensity, and the temporal evolution of this event in our high-resolution simulation is very, very similar to the observations. In fact, it's very hard to distinguish both of them. So another major benefit that you get if you go to the high resolution is you improve the representation of surface fields and orography, and this is shown here in this animation. So what you see is the Colorado headwaters, so the Colorado Rocky Mountains. If you go from 4-kilometer grid spacing to something which is more like a GCM, 100 kilometers, and you really see how these small-scale structures are disappearing very quickly if you go to coarser and coarser scales, and at the end you only have a large hill left at the GCM scale. So there are 4 different approaches to do convection-permitting modeling, and the one approach that I will talk about today is limited area modeling, and this is the most commonly used approach as well. The second one is the most rigorous one. It's using global climate models in convection-permitting mode, and this is, of course, extremely expensive. That's why people developed the third approach, which is using superparameterizations. So this is approximately 1,000 times cheaper than this approach here. And the fourth approach is stretched grid models, which is very promising as well. But we will really focus on limited area modeling in the rest of my talk. So one obvious challenge in this convection-permitting climate models is the computational resources. And I just wanted to give you a feeling how large they are. So let's assume you did a a transient climate simulation over the EuroCordex domain, 12 kilometer, 150 years, at a supercomputer, something like this. And you have the same computational resources once again, and you think, oh yeah, I did do the same simulation now in 4 kilometer setup. So I just wanted to guess how many years can you simulate with the same computational resources? So it's, in fact, 5.5 years. So it's less than 4% of the runtime that you get from a 12 kilometer model. So these kind of models are very expensive. So of course, you directly have to ask yourself, why should I do that? Where is the added value? Where is the gain if I do that? And I will come to this in a couple of minutes. So before I talk about the added value, I wanted to talk about the model setup and some other challenges. In fact, if you think about convection-permitting models, you of course have to ask yourself, which grid spacing should I use for my simulations? And there are only a few studies that tackled this question. And one really nice one is by Wolfgang Langhans et al. 2012, where they performed convection-permitting simulations over Switzerland in 4 different grid spacings, from 4.4 kilometer down to 0.5 kilometers. And the surprising results from this simulation was, in fact, that if you look at regional averages, for example, regional average precipitation, like it's shown here in this general cycle of precipitation, there's not a large difference between 4.4 and 0.5. So in fact, bulk properties are very similar in this kind of simulations. What's different is really if you look at the single cells, so if you look at the structures of the cells, you see that you get more and more small-scale structures, the higher you resolve, or the finer your grid spacing gets. So this hasn't converged. Another challenge is the domain size. So since our simulations, or the simulations are so expensive, people use pretty small domains. So these are just a couple of domains that were used in Europe. And small domains have 2 major issues. So first, it's very hard to assess the representativeness of your results if you're in a small domain. And the second is the spatial spin-up. So you need some space to spin up your dynamics and your physics in your small domain. And there is a really nice study by Erwan Brisson from last year. And what they looked at was how Graupel, a hydrometeor that they used in their high-resolution simulation, spins up if they have the inflow from this boundary here. And you see that you need approximately 400 or 500 kilometers to get it something like an equilibrium. So this is a really large spin-up. And if you're in this very small domain, you will never reach the equilibrium state, in fact. So that's why people started to use convection-permitting models on much larger domains. So this is a domain that we are using at NCAR with the 4-kilometer WRF simulation, and Ethan Goodman will talk about this simulation later on in these sessions. And there are also 2 other talks by Thomas Schwitthaler and Christoph Scheer later on that will talk about convection-permitting models on something like a continental scale. So the model physics are, of course, also challenging. So what's typically happening in convection-permitting modeling is that people use the setup for their physics from weather forecasting models. So they adapt the physics from the weather forecasting models to their climate models. So this means that the physics, most physics, haven't been tested on climate timescales yet. And this can, of course, cause some problems, especially if you think about cloud aerosol and radiation in your model. So if you directly resolve deep convection in your model, you resolve deep convective clouds, and these clouds are much more complex than stratiform clouds. So you have mixed phase clouds with a large variety of hydrometeors. All of them are interacting. There is radiation which is interacting or should interact with all of them, which it doesn't do in all the models. And of course, you also have aerosols that are interacting here. So this is a very complex system, and nobody really knows how to tune or set up those kind of systems. The second thing is turbulence. So for turbulence, this is the turbulence kinetic energy spectra. And for turbulence, we have basically 2 different theories. theory for the very large scales where we use Reynolds averaging in our traditional climate models, and another one for the very small scales below 100 meters, which is large eddy simulations where you just simply resolve the energy of the kinetic energy. And as you can see with our convection-permitting models, we're right in between, where there is not a solid theory for turbulence. And people are working on this issue, and the problem is that there are still not really schemes that are appropriate for this regime, or they're not really implemented or tested. And the last thing I wanted to mention is the soil vegetation atmosphere coupling. And here, just because you have high resolution in your atmosphere doesn't mean you have high resolution in your soil, because some of the soil properties, like the texture or the soil type, are very closely resolved. And on the other side, some of the coupling on soil processes are oversimplified. This is really limiting your ability of your convection-permitting models, and Sebastian Knist will talk about this issue a little bit more later on in the session as well. So let's come to the main point, the added value of convection-permitting climate models. And to start with that, I wanted to give you another animation. And what you will see is a typical summer day in the Eastern Alps. So it's this region here, where we have deep convection. And we will look at a 3-kilometer simulation, which explicitly permits deep convection, then a 10-kilometer simulation with a convection parameterization. And this is the observational data set. And I just wanted you to focus on the 10-kilometer simulation at the beginning, because what you see, it's starting to rain much too early, and it's very widespread rain, and it's low intense. This is very typical for large-scale models. But if you focus on the 3-kilometer simulation, you see that precipitation occurs much later, so much more similar to the observations. And the structure and intensities of these cells look much more realistic. So what we see here is really a shift in the regime, how convection is simulated in our models, from a very unrealistic regime to a very realistic regime. And this was confirmed in many studies already, that this added value exists. So this is not really one model. This is in multiple regions with multiple models. This was shown already. So the issue that we also heard this morning is if you just, so we have the very high resolution, if you look at hourly precipitation, for example, here from our 4-kilometer simulation, and something which looks very unrealistic from a coarser resolution simulation. The issue that we face is if you just sum up over a climatological period, you get bias maps like this. So this is just showing you the summer bias in precipitation in the United States. And I would argue that you can debate if there is added value or not. In some regions, you get improvements, others are deteriorating. And this is pretty typical. If you average over longer time periods, you smooth out the added value, and therefore you really should use special methods or look at specific processes to detect the added value. And one of these processes, which was widely studied already, is the general cycle of summertime precipitation. And what I will show you here is a map with the peak timing color-coded. So if you have a precipitation general cycle like this with an afternoon peak, it will be red, a noon peak will be yellow, and if you have something like a midnight peak, it will be blue. And this is how this looks like in the observations in the United States. So you have basically afternoon peaks in the east, afternoon peaks in the west, and in the middle you have this transition from afternoon regimes into nighttime regime and then early morning precipitation peaks. So this is well studied, because what's happening in the US is that you have propagating convective systems which start here in the afternoon, and then they propagate over the Great Plains and cause midnight peaks or nighttime peaks in the central US. So this is what you get from a coarse resolution model. So this is a typical coarse resolution model with 36 kilometers parameterized deep convection, and you see that in most places you peak somewhere at midday. You have something like a nighttime feature in here, but it's questionable if it's getting this for the right reason. However, if you now look at the 4-kilometer model, I would say this is a really large improvement here. So you get the afternoon peaks in the west and in the east, and then you get this smooth transition into nighttime peaks in the right place. So there is a clear added value, and I wanted to go a little bit deeper here. So what you see in this diagram is, again, the summertime diurnal cycle, and this is from Priscilla Mooney, who had a poster in the last poster session. And what you see here is the western United States. This is the observed diurnal cycle in summertime, and this is a large physics ensemble of WRF simulations with 36 kilometers. So basically what you see is the red, the green, and the blue are different convective schemes, but no matter which parameterization you use, you never get close to the observation, so you're always wrong. So if you look at a little bit more detail, you can split this up. The amount of precipitation is the frequency times the intensity. You directly see that you heavily overestimate the frequency of precipitation and underestimate the intensity. So it's just raining all the time a little bit. And if you look now at the 4-kilometer simulation, you see that the diurnal cycle is really largely improved here. This is because you get a large improvement in the frequency. You still underestimate the intensity a little bit, but I think overall this is a clear added value of the high-resolution simulations. Another area where people found added value is extreme precipitation. There's a nice paper from Nicolina Bann, excuse me, et al. From 2013, where they did a 2-kilometer convection-permitting simulations over the Swiss Alps. And what they found was that their convection-permitting simulation was nicely reproducing their observations. So this is the frequency and intensity was nicely reproduced, whereas the 12-kilometer simulation underestimated the intensity and frequency, especially of heavy events. The interesting thing in this paper is really if you average the hourly precipitation to daily precipitation, you don't see this improvement anymore. So now you could argue there is no added value, but if you look close enough, you really know that the 12-kilometer simulation gives you the right answer for the totally wrong reason. So you really have to look at the process level to see the added value. And there will be a talk by Michel Déqué later on in this session who will talk about extreme precipitation in France. So this is a slide where I wanted to show you that we don't only get added value in summertime precipitation, but also in wintertime precipitation. So what you see here is from a paper of Roy Rasmussen from 2014, and they aggregated precipitation over a winter season from the observations in the Colorado Rocky Mountains. And then they tried to reproduce this accumulated precipitation with a 36-kilometer model. And you see that we heavily underestimate the precipitation in this region. However, if you increase the grid spacing step by step, you really get closer and closer to the observations. So once you have 6 kilometers, you're very close to what you really observed. And this is, of course, very important if you think about the building and the melting of the snowpack in this region, and has large effects on the hydrology and snow and glacier modeling. So 2 slides on climate change signals. So there were a few studies who looked at climate change signals with convection-permitting models. And one of these papers is by Nicolina Bann et al., 2015, and what they did, they looked at the precipitation climate signal in Central Europe. So this is Switzerland, that you have an orientation. And what they saw is that the mean precipitation is significantly decreasing in their domain at the end of the century. However, if you look at extreme hourly precipitation, you see a strong increase, which is surprisingly pretty homogeneous. So what you see here is really a decoupling between the mean and extreme precipitation. And we see very similar results from our simulation in the United States, where you have a mean drying, for example, pretty significant in the central United States. But if you look at extremes, you still get significant increases in extremes. Another study, which is very interesting, I think, is from Kelly Mahoney, 2012. And what they looked at was the future of hail in Colorado. And what they found was that hail is almost vanishing from the surface at the end of the century. And the reason here is that the melting level high is increasing, so the hail melts before it reaches the surface. And this is something you really can do with convection-permitting models, because now you really have the small-scale convection explicitly resolved. And the last study that I wanted to highlight is again by Roy Rasmussen, 2014, and they looked at the water balance in this region here with a convection-permitting model, and what they found was that they have a net increase in precipitation in the future climate. So the future is the blue one. However, if you look at the runoff, there's not really a change in the runoff. So what's happening here is that this increase in precipitation is compensated by an increase in evapotranspiration. So this is really showing you that you really have to look at the whole water balance to understand how the hydrology in the region will change in the future. So if you just look at precipitation, this is really not giving you the total answer. So some final remarks. If I have to summarize this whole talk, I would say that convection-permitting models allow you to understand climate change on a process level. So we really can simulate small-scale processes. And this is really a large added value, I would say. And at the end, you can answer the question, how does the weather change due to climate change? So these models are actually on the resolution of state-of-the-art weather forecasts. So this is really enabling us to look at climate change from a whole different perspective. Some major challenges that I wanted to highlight. The model physics, I already talked about that. I think we really have to rethink or retune our model physics to have the largest added value from convection-permitting models. Model uncertainty assessments, this is very, very difficult because they are so computational demanding. You can only afford 1 or 2 runs, so it's very hard to assess uncertainties in these models. Observational data sets and model evaluation, there are only a few regions on the globe where you have suitable observational data sets to evaluate your model. And the last point is the big data and future high-performance computing. And the point that I wanted to make here is that I think at a single institute, you cannot really solve this kind of challenges. So you really have to work on this as a community. And the good message here is that our community is growing. So this is the number of publications from 1990 to 2015, which are talking about convection-permitting or convection-resolving climate simulations. And you see we have a really exponential increase in publications. So I think our community reached a critical point where we really should start working together. And CORDEX, I think, is the right framework, can provide the right framework to do this as a community. And we are hosting a GWEC-sponsored workshop at Anchor where we will, it's a 3-day workshop where we'll talk about convection-permitting climate modeling. And if you're interested in joining us, we would be very happy, and we are currently accepting abstracts. Thank you very much.
I think we have time for a few questions. Samuel? Okay, we can start here, I guess.
Thank you. Very interesting talk. But I'm afraid, so this deep convection is only the first threshold that we are going to overcome, because there's very important shallow convection that has scale of 100 meters. And that will be the next, which is very important for climate and exchange of energy between atmosphere and surface.
I totally agree. So this is what I maybe forgot to talk about it, but in the turbulence parameterization, this is part of the turbulence parameterization as well. So this is a really major challenge, but I think still to resolve deep convection is a very large step forward. And of course, we have to think about shallow convection as well.
While she brings the microphone to Samuel, I have a question.
Oh, yeah.
Why are they called convection-permitting and not convection-resolving?
You know, I think I should talk about this as well. Some people are calling them convection-resolving. Some people say cloud-resolving simulations. I call them convection-permitting.
And what's the difference?
I call them convection-permitting because you start to allow convection. You don't really resolve fully convection, because convection is happening on much smaller scales, of course. So you start to permit convection. But it's, of course, just a flavor, I guess.
Someone.
Concerning the added value you have shown for the extreme precipitation, for the intensity, and for the peak, the afternoon peak of the convection, some people say that we could achieve this by improving parameterization of the convection in a non-convection permitting model. So what do you think about that?
So no, I think there are some papers about convection parameterizations, state-of-the-art convection parameterizations that actually can resolve afternoon peaks. I think maybe you can do the Diurnal cycle. I think you cannot do the intensities, because intensities, you see the structures of these cells are so small. If you're working with a large or coarse-resolved model, I think you have no chance to resolve the intensities that you really get in nature. So you really have to go to the high resolution.
Christoph?
Well, I like that Filippo actually brought up the issue of terminology.
Yeah.
I'm among those that call it convection resolving. I think the term convection permitting is a little unlucky. I think if you look at other areas of modeling, we would not call, let's say, a ECMWF model. We would also say this resolves baroclinic eddies, but of course it doesn't resolve all baroclinic eddies. Or an eddy resolving model in the ocean does not resolve all eddies in the ocean. So I think it is fair that it is a fair comment that one actually can say convection resolving, also appreciating that we don't resolve everything.
Yeah, totally agree.
Okay, some controversy. There you go. Actually, I have another question. You said in the last slide that you have to retune some of the parameterizations. Since we are kind of getting into this now, we have a non-hydrostatic version of our model and so on. So what are the key parameterizations that you have to retune? Or
So
what did you exactly mean
I think
by
you
this?
really should be careful with the turbulence. This is one issue. And of course, the microphysics normally get much more complex. So for example, you add something like Raupol to your microphysics.
Yeah.
I don't know if you do this.
Yeah, we have like 5 variable scheme, whatever. But what is it in those?
Now, for example, if you introduce a new hydrometeor, you really have to have also the radiation interaction of the micrometeor, which is often really missing. So sometimes you have clouds and there just radiation is going straight through them if you're unlucky.
Hopefully not. Well,
Yeah.
so anyways, the microphysics and the PBL schemes, essentially, the turbulence scheme.
Microphysics, PVL, shallow convection, I think this is really a major issue as well.
We have time for a few more questions, if there is any. Okay, if there are no questions, thanks very much, Andreas. Very nice talk.
Spatial resolution on the characteristics of precipitation in the Maritime Continent. This is a work I've been doing with Alejandro Di Luca and Jason P. Evans in my previous institution in Australia. I'll try to also offer an overview of an application for these sort of simulations. So to begin with, I'll introduce a little bit the region, because many of you might not be familiar with this region. The Maritime Continent is this archipelago between the Pacific and the Indian Ocean, and it has very warm ocean surrounding these islands with very complex topography, and there are like thousands of islands of different sizes. So, and what happens in this region has implications globally. The warm waters put water moisture into the atmosphere, is brought up into the atmosphere, and so adds energy to the upper troposphere, and that contributes to the water circulation, and so has implications for the large-scale circulation. So the errors that occur in this area has also repercussions in the large scale. Unfortunately, what happens in this area is that many models have a strong bias. This is just an example of one model in the Maritime Continent at different resolutions, and we see this very dry bias over the islands and the wet bias in the surrounding ocean. this is just one model, but it's common to many other models. They tend to have very bad precipitation in this area. And one of the main reasons for this is that they don't capture the diurnal cycle, which is very important in this region. And this is just an image of Himawari satellite, a video, and we see deep convection just in the afternoon. There is almost cloud-free islands during the morning, and as soon as the sun passes by, we have this deep convection happening in the islands. So this region is characterized by convection, which is dominating precipitation, very strong diurnal cycle, very complex topography, warm ocean, and therefore land-sea contrast, and very, very particular local circulation. So it's a great candidate to benefit from increased resolution. So as part of a project that we did to understand what are the implications of urban areas in local precipitation, we ran these convection-permitting simulations over Jakarta and over Kuala Lumpur at 2 kilometers. It's roughly 300 by 250 points located in this area here, and they're embedded in a 10-kilometer and then in a 50-kilometer domain that encompasses the whole Maritime Continent. These are driven by error and stream, and we have 5 years of data with a 2-month spin-up. And we use all the results I'll be showing is an average over the 5 years, just to give an idea. I will focus my talk in this area, but what we get for Jakarta is fairly similar. So these are the mean precipitation biases of WRF in this region. And this is at 50 kilometers. We have a very strong positive bias of the ocean, and it's not doing so bad of the land areas. If we zoom in into the 10-kilometer domain, we see, well, of course, the same pattern with this wet bias of the ocean, and slight improvement in the 10-kilometer. But there's really no difference over land. There's not really a big improvement over land in this area. If we look at the 2-kilometer, this is over the Malay Peninsula, where Kuala Lumpur is located. We see that there is a significant improvement in the mean bias over this area, especially over the ocean. And when we go to 2-kilometer, there doesn't seem to be a big improvement. There's actually some overestimation of the mountainous areas. This is compared to TREAM, which is 25 kilometers, and CMORPH. We chose the smaller bias between the two to give an idea of the spread between the different observations. And we know that these products have some problems in the mountains. But if we look in general, there doesn't seem to be a neat improvement. Of course, this is just mean precipitation, and we don't want to resolve just mean precipitation. We want to look at all the characteristics to understand what is happening. If we look at the timing of the diurnal peak in this area, and as I said, this is TREAM. This has only a 3-hourly frequency, so it's a bit coarser than the other, and the other 4 are hourly. This is CMORPH at 8 kilometers, 50, 10, and 2 kilometers. The white areas is where there isn't really a diurnal cycle. The difference between the maximum and the minimum, the ratio, is smaller than 2. So we masked them because we consider there isn't really a diurnal cycle in those areas. And I think it's nice to see that there's some regions where, well, in general, there is an improvement between the 10K and the 50K, and that's very clear. But also when we go to the 2-kilometer domain, we see that there is an improvement in the timing of the maximum precipitation. There is basically a delay of the maximum precipitation compared to the 10-kilometer, which is consistent to what we see in the observation, especially in CMORPH. If we look, for example, this area here in Sumatra, we see that it's occurring much later in the 2-kilometer domain than in the 10-kilometer domain. And the same occurs for the Malay Peninsula. There is a later peak in the maximum precipitation. If we look at the amplitude of the diurnal cycle, so the maximum minus the minimum, we also see that the increase in the amplitude in the higher resolution is clear compared to the others. We basically have almost a flat diurnal cycle in the 50K, and as we increase the resolution, we get a stronger diurnal cycle in terms of the amplitude. And it is consistent with the CMORPH. We tend to overestimate some of these this feature in some mountainous areas again, but in general, I think there is a better representation of this feature. This is another way of looking at the diurnal cycle of precipitation. This is CMORPH, and this is a cross-section of the Malay Peninsula where Kuala Lumpur is located. This is a Huffman plot where we have the time of the day in the y-axis, and this is longitude. In green is where the land is located. So it's very clear where we have this maximum of precipitation in the night and early morning, and then it appears in the afternoon of the island. It propagates from the coastal regions towards the interior of the peninsula. If we look at the 50 kilometers, we do resolve this sort of a pattern, but it's clearly occurring much earlier than in the observation, and it's really weak. We don't see the values that we see in the observation. It's just a weak diurnal cycle that is occurring too early. Moving into the 10 kilometers, we have it a bit later again, so we can see the shape of the diurnal cycle pattern that we see in CMORPH, but again, the values are too weak. We do capture the ocean well in this area, but when we go into the land, we see that the peaks are not reproduced in the model. Moving into the 2 kilometers, we see that the pattern is not exactly the same. We have a bit more noisy pattern in the land, but we have the same values. We have very similar values in this area. And it's interesting because this means that we're starting to get the local circulation better in this area. We have some overestimation of the ocean that is intensified with a 2 kilometer domain. And also, if we look at the timing, again, is more similar to the CMORPH, to the observation-based data set, in that it's later in the afternoon. This is the cross section again. In these plots, I'm showing the cloud mixing ratio for this area, together with the winds, the local winds. So it's the horizontal and the vertical winds at 8 in the morning and 5 in the afternoon, to give an idea of what is happening at different times of the day. And in the 50 kilometers, we basically have no local circulation. We just have winds coming from the east that goes over the land, but we don't have any sort of a local circulation. And also, we don't see any cloud mixing ratio this time of the day. For the 10 kilometers, we start to see some patterns created by the local topography in this area. And when we move to the 2 kilometers, we see the land breeze, the reversal of the winds, and some subsidence in the interior of the peninsula that is occurring. And I don't show the ocean here, but this is going back into the ocean and created the convective system of the ocean. If we move into the 5 p.m. time, we see there is some sort of a sea breeze pattern with some of the circulation, but it's not very strong. It's just a very weak convergence of the land. Moving into the 10 kilometers, it's much clearer on the western part of the peninsula. We see this accumulation of a cloud mixing ratio of the western part of the mountains, and this is translated into precipitation in this area. And on the other side, basically, we don't see any circulation. We just see the main wind is coming into the mountains and then lifted up and located in the same area. If we go to the 2 kilometers domain, there is a much nicer convergence from both sides of the peninsula, and the cloud mixing ratio is spread across the peninsula. And this translates into rainfall across the entire peninsula when these clouds are formed in the afternoon. So I think that this is telling us that even if we don't capture the mean precipitation accurately or better than the 10 kilometer, there is some hints that we are better reproducing the local precipitation, and this is very important, the local circulation, sorry, and this is very important in areas such as the Maritime Continent, where the local circulation is the main driver for precipitation. So this is just a look at the quantiles to give an idea. Here I show some results for Jakarta as well, so it's the precipitation quantiles over these two areas. And we see that despite the fact that we are overestimating the quantiles from CMORPH, which is the green line, the black line, the one-to-one line is stream. We are overestimating at 2 kilometers, but it looks like the shape of the curve is better. Of course, this is just one region, and we have to take into account that there is a significant difference in the resolution of the observation, which is of the data set, that also play a role in these plots. But this is giving us an idea of how we are better capturing the trend or the linearity of these quantiles. And to conclude, just a final comments. I think the improvement of the mean precipitation is still unclear. And this might be due to the observation we're using. There's differences in the resolution, also in the observations, and we know that in some complex topography areas these products are not so good. But I think I showed some evidences that the precipitation characteristics are more realistic when we go to high resolution. And this means that we are more confident on what we're doing. It's not probably giving us the right mean precipitation, but the underlying processes that give us that precipitation are more realistic at high resolution. And these results took us to the next steps, and now we're thinking of using different SSTs, because it's the main driver for the Landsea contrast and triggering the Landsea bridge, which in turn triggered the convection in this area. And also increasing the resolution beyond 1 kilometer to step away a little bit from the gray zone and try to better resolve convection in this region. That's all. Thank you very much.
Time for a couple of questions. Actually, I have one. It seems that one of the big things about this convection resolving or permitting models is to capture better this diurnal cycle of precipitation. Now, my question is, from the climate point of view, is it worth spending 100 times more computing time just to get the diurnal cycle better?
I think
why is it so important to get the diurnal cycle better? This was, from a climate point of view, was never really entirely clear to me.
I think if our aim is to better reproduce or try to reproduce more realistically the processes underlying the climate, then it is. If we look at the mean precipitation, there might not be an improvement, but
there are many processes that we don't do well.
Yeah, but if you want to look at other statistics rather than just the mean, then it might be important. On the other hand, there's also, depending on the region, there might be regions where this diurnal cycle in terms of the climatology is also very important, because it has impacts for the local communities depending on the intensities of the rain, because you look as well at the diurnal cycle, it's not only the shape of the diurnal cycle all the time, but also the intensity of the diurnal cycle. So if we look at subdaily precipitation, it has huge impacts for the local impact people that want to address what is going to happen in the future with this diurnal cycle.
No, I already have microphone.
Here, sorry.
I actually agree with Filippa. To look at this new, so exciting development from the pragmatic point of view, so we heard two very nice presentations with fine resolution, and really what we could achieve at this time, so we will resolve dynamic, a little bit better, we will resolve dynamic processes. Do you want for climate application to resolve any convective cell? I don't know if this is possible. The second, So we, of course, resolve dynamical part of convection. We define incorrectly vertical velocity at this resolution. It means we incorrectly describe the whole microphysics. And how precipitation will work on this background, it is another question. So we link climate modeling to cloud resolving modeling. So there was a big community that modeled cloud microphysics and cloud dynamics from other side. So this community works in 1 kilometer resolution for decades already. So how to better overlap these two? So should we really resolve any convective cell, which will be very difficult? And what should we do with microphysics that is not approximated and will not be approximated for another decade with that resolution what we have, maybe longer. It would be nice to hear the bigger picture, what you expect from this effort, which is very exciting.
I don't think I quite get the question. I will
Actually,
reply.
Actually, we're not the only one, but
I think I will reply to the first one. I don't claim that we should resolve all the convective scheme of the convective system, of course. But I think if we go to higher resolution, there's some evidence that we are representing the physical processes better. And if we have the computing time to do it, then we should go towards that. We don't at this moment to do it. But I'm not claiming we have to resolve all of them, of course.
This is a very complicated issue, actually. We don't have time to get into this, I think. Okay, thanks very much,
Thank you.
Daniel. Michel Déqué, old friend, many conferences together.
So this is my contribution to the debate of convection permitting versus convection resolving. If you look at the printed program, it's written convection resolving model. And here, if you read on the screen, it's convection permitting. So this means that I will not spill my blood to decide whether we are really permitting or resolving convection. So the target of our study is, like the presentation this afternoon, is on precipitation and more precisely on extreme precipitation, with a focus on hourly to daily precipitation, so it's small scale in time. The season I will focus on is this. The red, okay. Is September to December, and here is a map of south of France with the Mediterranean Sea here, the Alps there, and here another mountain named Massif Central. And in this region, we have tried to define objectively a subregion here in blue, which has been defined in the following way. The whole domain has been divided into 50 by 50 kilometer boxes, and we retain only those boxes for which the maximum daily precipitation rate in an observed series is more than 300 millimeters per day. And very nicely, instead of having boxes spread everywhere over the domain, we have a consistent area here that we will name 7. Geographically, 7 are just this part, but typically we will use 7 for the whole blue part, and we will make statistics on that region on which we experience almost each year a very dramatic event of heavy precipitation with flash floods which are induced by this. The physical phenomenon behind this is the fact that in autumn we have warm and wet air coming from the Mediterranean Sea, which penetrates into France, and then there is this mountain as a barrier, and sometimes thunderstorms due to this instability and this strong moisture are blocked by the orography and produce heavy rains. So this is a phenomenon on which we will concentrate in the next minute. The presentation will be in two parts. In the first part, we will compare validation against observation to be sure that what we are speaking is close to reality. And in the second part of my talk, I will compare a scenario versus a reference simulation. We will use different numerical models in this study. So in fact, modeling is a chain. Here we have the CMIP5 simulation, the AO-GCM. In our case, this is CNRM-CM5. In between, we add another GCM at higher resolution and with corrected SST, so that the transition from CMIP to EuroCordex is smoother than if we jump from the 120 kilometer to the 12 kilometer, and if we introduce SST biases in our simulation. Here we have the RCM Aladdin, which is a EuroCordex model used in EuroCordex. However, in this presentation of today, it's not the official EuroCordex simulation that will be used, but a sub-EuroCordex on a smaller domain, including France and neighboring countries, but it's not the whole EuroCordex domain. This allows to save time in computation. And this Aladdin model will drive the AROM, which is a non-hydrostatic RCM, which is based on the same modeling core, but it uses non-hydrostatic equation and specific physical parameterization. Its resolution is 2.5 kilometers. And the domain here is in black. It's southeast France. It includes part of the Alps, the Gulf of Lions here, part of Mediterranean Sea. And the Cevennes area is here that I mentioned. So it is in the middle of the domain, and as Andreas explained to us before, we need to have at least 100 kilometers between the boundary and the area we are studying. Otherwise, we can claim our model is non-hydrostatic. It's, however, a hydrostatic model because of the impact of lateral condition, because Aladdin is a hydrostatic model. So we will concentrate on this region here. And first, make a validation against observation. The observation we have available in France is the COME4 reanalysis. It's a reanalysis at 1 kilometer resolution, and which provides hourly precipitation for a 10-year period. It uses a radar network and as much as possible daily hourly and daily rain gauge. So we have this database, and from that database we extracted the Cevennes area, which is here. Here you have the city of Nîmes, Bolène, Montpellier. This is typical, the area of our study. In the model validation, there is no GCM. We have replaced the two global GCM by ERA interim, which is at resolution 70 kilometers, which is close to the arpège resolution. Of course, it has no SST bias. And it drives Aladdin and AROM. And in the following, I will mention Aladdin and AROM, and you must have in mind that Aladdin means RCM at 12 kilometers, and AROM means non-hydrostatic model at 2.5 kilometers. Here is the comparison in precipitation over the Cevennes domain. Here on the left is daily precipitation, and here is hourly precipitation, and here is probability. So the heavier the precipitation, the lower the probability. And here you have return period of typically 40 years. In black is the observation, COME4. In red is AROM. And in blue is Aladdin. And you can see as for daily as well as for hourly, AROM and Aladdin, AROM and observation are nicely together till return period of 4 years, or probability of occurrence 10 minus 3 to 10 minus 4, but from 10 minus 4 to 10 minus 5, which are very rare events, then we can see that the model underestimates the intensity. The hourly intensity is 50 millimeter here, whereas it's 70 millimeter per hour over the Cevennes, which is a very high value. For daily accumulated, here it's the same. We have a similar behavior with about 250 millimeter per day for the probability of 10 power minus 5. but 350 millimeter. But if we compare with Aladdin, Aladdin is clearly underestimates this extreme precipitation, even at the threshold at this quantile. This is a quantile 99%. 99% quantile is okay, or more or less okay for different model, but if you go to 99.9, 99.99, and 99.999, you can see the divergence of the different models. So we can be more or less confident in what, at least more confident in what AROM provides us versus Aladdin. However, one might suspect that this is an unfair comparison, because in AROM we have much more points than in Aladdin. We have 25 more points than in Aladdin, and we count our probability by counting grid point by grid point inside a box. So one might think that this is unfair. This is not, in fact, because if you can compare the statistics of Andorra and the statistics of France, and you can put on the same diagram, although there are much more people in France than in Andorra, but you can, however, make comparison even if the size is not the same. But to convince this, I have made this analysis in which COME4, Aladdin, and AROM has been averaged over 50 by 50 kilometer boxes. In this case, you have the same number of data, whatever you consider observation, AROM or Aladdin. And you can see, if you compare to the similar curve here, in which the data are not aggregated, this is individual grid point and these are averages in boxes. You can see, of course, you get less precipitation if you average in a large box, because the very heavy precipitation have a scale smaller than 50 kilometers. But you can see that the conclusion you draw from this is still valid in the fact that AROM and COME4 are in agreement till this level of precipitation. This is 10 minus 4. In the previous slide, it was 10 minus 5. I cannot calculate precipitation to 10 minus 5 because I don't have enough boxes to count the probability. Now, second part of my talk is the climate change scenario. So here we will consider a reference simulation of 12 years, 1989 to 2000, and a scenario of 12 years based on the worst possible scenario to maximize the signal-to-noise ratio. One might think that 12 years is not enough for climate, but here we are comparing a driving model and its slave. So in this case, there is no interannual variability. A rainy day for arpège for Aladdin is also a rainy day for AROM. So in this case, we can make, even with 12 years, it's reasonable to make a comparison AROM versus Aladdin. What would be not reasonable would be to say, this is the climate change, because it's only 12 years. And we will have Aladdin, AROM, and also another simulation that unfortunately I will not present you because the chairman made me the signal that I had only 3 minutes to conclude. So here is a scenario. The scenario is, so you have the blue for Aladdin and the red for AROM, and the dash is for the scenario, and the solid is for the reference. And you can see that according to Clausius-Clapeyron formula, you have higher temperature and you have heavier precipitation. And the increase for that quantile, for the 99.999 quantile, you have an increase by about 50%. And here again, an increase by about 50% of the quantile, which is not nothing. But the funny thing is that if now we look at daily precipitation instead of hourly precipitation, we have a nice phenomenon which is local to the 7, is that in which we have an increase of extreme precipitation with Aladdin, but a decrease with AROM. And when we mention the idea of added value of some model in climate change, and added value would be the fact that we might get a different response. So I skip just this. If we make the synthesis from different accumulation, from this is 1 hour accumulation, 2 hour accumulation, 24 hour accumulation. Here you have Aladdin, and you can see here you have the probability difference. Green means the probability increases, red means the probability decreases. For low precipitation, we have a decrease in probability, and for high precipitation, we have an increase in probability. This is the case of Aladdin. So whatever the time scale you consider, the extremes are increasing. If you look at Arom, it's different. With Arom, we have an increase in probability for hourly or 2 hourly accumulated, or up to 12 hourly accumulated, we have an increase. But beyond, we have a decrease even for the heaviest precipitation. And my conclusion is that we need convection permitting, and by the same way, convection resolving climate models for 2 reasons. Because if we look at observation, we are closer to observation, so we should be more confident in something that it's closer to observation. And also because in some cases, we can get an opposite response between the driving RCM and the driven GC and the driven convection permitting model. This is not the case of the whole domain. This is the case for, I will not have time to display the full map, but in the 7 we have an opposite response, but it's not the case of the whole domain. And I will not claim that the response to climate change is a decrease in extreme precipitation, but in the special case of 7 area and for daily precipitation, we have a decrease in the extreme with convection permitting model. And another point that I have not time to mention, I can just mention the result. We have repeated the experiment, but instead of running Arom as a long 12-year simulation, which takes many months, we have run sequentially. We restarted the simulation every 1st of July. And so we have a sequence of 6 months simulation that can be run in parallel, and we found no change in the results. So this is a nice news, because from a practical point of view, as was mentioned by Andreas before, it's very costly to run convection permitting model. But if you can run the season in parallel, you can save some time in your computation. Thank you.
Maybe just one quick question, if there is one. Here? Ah, there. There is.
Oh,
there
okay.
It's just a comment that maybe the model is even closer to observations, because I think you said that the observations were at 1 kilometer. And the model is at 2.5. So if you would aggregate the 1K to 2.5, and the model, I mean, both the black curve would go towards the red one.
Here all models have been aggregated at the same resolution of 50 kilometers. And as you can see, there is a good similar behavior between Arom and observation, whereas the 12-kilometer resolution model does not have enough precipitation.
But I mean that in the individual grid points, the comparison is not fair for the 2.5 in the sense that you don't expect to give information at 1K, but at 2.5. So it's not underestimating the intensity. Maybe it's doing perfect. Because, yeah?
It did it. In fact, we could say that if we model at 2.5 kilometers, we even not claim that we give information at 2.5 kilometers. We know from our models that the phenomenon that they resolve correspond to 5 by 5 grid point at least, and we not claim to have an accuracy of 2.5 kilometers in our simulation. But the phenomenon occurs at that resolution, and it's better to use that resolution to resolve rather than 12 kilometers.
Thanks, Michel. I think we need to move to the next presentation, Sebastian Knist.
Yeah, hello everyone, and yeah, thanks for the opportunity to talk about our current study on added value and land-atmosphere coupling in WRF convection permitting climate simulations over a Middle European domain. And as the title already suggests, this talk is basically divided in two parts. So the first will be about the convection permitting WRF climate runs we are doing, and yeah, it will be about an evaluation of precipitation and yeah, to show where to find added value in these runs. And the second part will be about yeah, an investigation of land-atmosphere coupling in these runs. So, to introduce yeah, the topic again, so yeah, what do you expect from a higher model resolution? Of course, with finer mesh size, yeah, we better capture the heterogeneity of the land surface, characteristics, topography, etc., and also better capture mesoscale atmospheric processes. And yeah, while the 12-kilometer CORDEX simulations compared to the 50-kilometer CORDEX resolution already showed improvement, for example, yeah, in the intensity of precipitation or the spatial distribution. Yeah, the further big step in atmospheric modeling is the resolving of the deep convection. And yeah, for our runs, we use a mesh size of 3 kilometers, and this is what our domain and setup looks like. So with our 3-kilometer domain, we cover here large parts of Middle Europe, and this domain is directly nested in a EuroCordex domain with 12-kilometer resolution. And yeah, we run with the same setup for both simulations, so the driving and the high-resolution domain, except for the switched-off convection scheme in the 3-kilometer resolution. And we run for yeah, different time slices here, driven by error interim data, yeah, that capture most of the variability of the Middle European climate. Coming to the evaluation of precipitation, I first yeah, want to give an example of typical precipitation events compared in both resolutions. So this is yeah, a nice pattern of a frontal system moving through the model domain. Yeah, in winter, this is hourly precipitation. And what you can see here is that, yeah, except for some yeah, local differences in the intensity, the overall pattern and amount of precipitation is quite similar in both resolutions, at least if you don't look at yeah, areas with steep topography, for example. But this picture yeah, looks quite different if yeah, you pick a typical situation in summer when convective processes plays a major role. This is here a day in June, and you see that the 12-kilometer in the 12-kilometer resolution, yeah, much more precipitation is generated, but the local intensities are higher in the 3-kilometer simulation. So these were just example of single events, but yeah, with almost a decade of simulated time, we have the opportunity to look at the yeah, overall precipitation statistics on a sub-daily basis. So we also compare based on hourly values, and as observational reference for that, I want to show here, we use here the rain gauge measurement station data from the German weather service. Unfortunately, the contrast is a bit weak, so there are overall 1,000 stations in Germany. The blue dots indicate stations with an altitude below 400 meters, and the green ones over 400 meters, and the red ones, I think, over 1,000 meter altitude. So, and this is what the yeah, mean diurnal cycle looks like. So, and this is the average over all stations for the whole time period in summer, and the observation here is a blue curve. The green curve is a WRF in 12-kilometer resolution, the yellow in 3-kilometer resolution, and interpolated the 3-kilometer on the 12-kilometer grid. Yeah, what you see here is what you already yeah, saw before in some of the talks, that yeah, the onset of precipitation is a bit too early compared to the observations, and you have yeah, a wet bias in both resolutions, which is a bit larger during daytime for the 12-kilometer resolution. And also, coming back to the timing of the maximum precipitation in the afternoon, yeah, there's already a slight improvement for the 3-kilometer resolution compared to the 12 kilometer, which is a bit closer to the observations. And yeah, this shift is also seen when taking all model grid points into account. So here for the entire domain. But it looks different if you look at different regions. So for flat terrain, the differences are not so large. Or when you look at mountainous regions here, such as the Alpine domain, both the shift in timing of the maximum, as well as the amplitude, the differences are larger. So, so much that. And looking at the daily precipitation statistics, so here the hourly precipitation intensities, that's the case where you can see the added value most clearly. So here again, the blue curve indicates the observations, the green one, the 12 kilometer, and the yellow one, the 3 kilometer. And you can see that the wet bias in the 12 kilometer resolution mainly results from too much light precipitation, whereby the heavy precipitation events are underestimated. And here again, the 3 kilometer, even interpolated on the 12 kilometer grid, performs much better. Of course, the differences are larger in summer when the convective processes play a major role, but also in winter, at least for the extreme precipitation values, also the 3 kilometer shows improvement. To summarize that, it's mainly, we confirm the results that have been seen, for example, for other studies like Ken et al. Or Ban et al. That's a typical phenomenon that you have too much light precipitation in the 12 kilometer, you get the extremes better in the convection-permitting resolution. So coming now to the second part of my talk about land-atmosphere coupling analysis. So land-atmosphere coupling is a quite comprehensive term for a lot of processes, feedback processes and interactions between the land and the atmosphere. And there are many different ways to quantify its strength. So we focus here on the soil moisture temperature coupling, which is highly relevant, for example, for the evolution of heat waves. And a valid method to quantify its strength is to look at the correlation of latent and sensible heat flux. So areas of weak coupling would be indicated in areas where the correlation is positive, so where we have an energy limited system, and strong coupling in areas with negative correlation, which are soil moisture limited. And if you apply this method, for example, here for FluxNet flux measurement stations all over Europe, this gives you the following picture. So you have mainly strong coupling in southern parts of Europe and weak coupling in northern parts of Europe. There's also a poster on that issue, also comparing different CORDEX simulations in terms of coupling on Thursday. So what does coupling look like for our simulations? So here the correlation of latent and sensible heat flux is shown for the individual summers of the individual years. And you can see a large interannual variability, which are consistent with the weather conditions in the individual years. So, for example, if you pick out these very two contrasting years, 2002 and 2003 in Middle Europe, you can explain the differences you see there with here for 2002 with very weak, overall weak coupling, with very, this year was very wet and cloudy, compared to that the very hot and dry summer 2003 in Middle Europe, resulting also in a the prominent heat wave in August 2003. And you can see here for almost the entire domain very strong coupling, except for the high alpine region. And as I said, there are different ways to quantify coupling strengths. Another method, for example, also includes the soil moisture. So here in this case, the standard deviation of soil moisture and the linear regression of soil moisture and latent heat flux. And this gives mainly the same picture of, for example, strong coupling in 2003 and weak coupling in 2002. What you can see here in addition is a stronger contrast between the individual land surface types. So the strongest coupling you can see here for areas with grasslands or crop compared to areas with forest, for example, where the coupling is a bit weaker. And of course, since we have, again, both resolutions, we can compare them for the year 2003 as an example for both methods. So here the correlation method, and here the method that was introduced by Diermeier et al. And what you can see is that in the 3-kilometer resolution, there's a slightly stronger coupling compared to the 12-kilometer resolution. But it's important to note that this must not be necessarily the reason or the cause of the higher resolution of the land surface, but more likely also a consequence of the slightly drier conditions in the 3-kilometer run, as we have seen before, or the other way around with the slightly wetter conditions in the 12-kilometer run. And this is still under investigation. So how do the individual land surface characteristics and its resolution affect the land surface coupling and thereby also the atmospheric processes? So coming to the summary, we confirm the results that have been shown before. So really the added value of the high convection-permitting resolution is most clearly seen in the sub-daily precipitation statistics. So as in our case, we look at the hourly precipitation statistics and the diurnal cycle. And when the land atmosphere coupling analysis shows a large interannual variability in terms of coupling strengths for Middle Europe, which showed a slightly stronger coupling signal in the 3-kilometer resolution. And as I said, what is currently ongoing is further investigation of the coupling process, also related to the resolution effect. Thanks for your attention.
Okay, so we do have time for 1 or 2 questions. Actually, I have a question. When I started doing regional modeling, or even now, one significant problem was that of so-called numerical point storms. So sometimes our models in the summer especially, you get this really intense, 50 centimeters of rain in one day or something. And these were not very physical and were related to this sort of process of self-feeding effect. And at least in my experience, they were mostly due to the large-scale rain, not to the convective rain, because the convective rain has a mechanism for stabilizing the profile, while the non-convective rain has less of a mechanism. So I was wondering whether with these convection-permitting models, there is also an issue of numerical point storms, like when you get at some grid point, 200 centimeters of rain or something like this. Do you know if there is such a...
I must admit I haven't looked into that in too detail, but I see from some other simulations we also saw some of these examples.
Say again?
I haven't looked in detail into that, so I have no additional plot or so for that. But if you, we've seen that also in
some really very strong. So I don't know, Andreas, is this a problem you think, or Christoph? Or?
We see the 12 kilometers, but we don't see the 3 kilometers anymore.
I have the same experience.
So the grid point storm is a key.
All right, I think we have to resume at 3:45 sharp, because at 5 o'clock this room is needed for another meeting. So please come back at 3:45 sharp.